All right, I'm recording now.
Tools on it. And I'll show you which one do you this is how you can manage all of our environments. So like Docker containers, if I dive into this is like a Docker image file basically. And then finally, when you can deploy it as an API, I can just use a very simple like JSON API to make predictions, submit my data as parameters, and then get my prediction back out. And you can see a couple of the like wrappers in Python and stuff like that. Okay. Questions so far? Okay. Yeah, feel free to take yourself off mute and ask questions too. I'm kind of working around here. So by now, everyone should have received an invitation to this to school. And you should do that. This full screen. With a README file and any files that we might have in this particular workspace. We get that in the repository. Okay, you can see it's blank. I haven't added anything directly to this repository. But what I have done is associated our GitHub repository for this week. The latest in our workspace. Okay. Again, down here to add. Okay. Always gotta make it a second, guys. First name. And select the GPU option here. Again, change your first name. Type something that's known to you, so you know what notebook you're using. Select the GPU and the hardware tier. Make sure you clicked on Jupyter Lab, and then click Launch Jupyter Lab Workspace. That'll automatically open a new tab as it takes a few seconds to provision the server that your Jupyter Lab instance is going to be running on. And you can see the, like, what I call the Domino's pizza tracker visualization. It's queued up to get a job. It'll schedule where to deploy it, prepare the environment, build the environment, pull the latest content from the Domino and GitHub repos, and then launch everything for us to use. Double check here. We're not missing anyone. Cool, cool. It'll take a minute for everybody, so apologies for the delay. But the reality of using things that aren't Colab can take a little bit longer. No, Trista, you don't have to fork the repository, right? Cool. Make when you're yeah. Yeah, and while we're waiting, I think you probably noticed there's another kernel here. So once you guys are done with the program and you have some spare time, not applying for jobs, Julia is a really, really great programming language. C, sweet. If anyone needs additional instructions, let me know. Might take a few more minutes for things to launch. Things to launch. So in the repositories like you have been doing this week, what I'm going to ask you to do is if you want to fork the lecture notebook for today. What you can do, actually, I just okay. Hey, I've only got 4 people that have told me that their Domino workspace is launched. Make sure you let me know if your Domino workspace is launched. Respond in Slack, please. When we're done with the lecture, and I'll go over this again at the end of the lecture, I'm going to ask you to, when you can work on the fork for your assignment this week, this afternoon, and then create a review request inside the documents. Great. I think we've reached quorum on people having access now. So go back to this page on your Jupyter Lab environment. It's just that you have, that's all, where you don't have to worry about the environment. You can just launch a Jupyter notebook and work. So very similar to SageMaker. I don't know what cloud it operates in. It probably operates on top of AWS or one of the other big providers. Okay. I'm not sure how many of you have seen Jupyter Lab before, but it's very similar to Colab. We're going to go up to the home repository, click on this little home button up here in the top left-hand corner. Then the stuff that we pulled from GitHub is under the repos folder. So click on the repos folder. Then click on DS, Unit 4, Sprint 4, et cetera, et cetera. Bing. And then you should see the repository folder, DS Unit 4, Sprint 4. Click on that. Then go to Module 1, RNN. Click on that and launch the notebook. How do I get to files? I'm not. And feel free to take.
Okay, all I've got is across the top, files running in clusters.
Did you launch?
Yeah, no. Oh, lab. Is what I need.
Jupyter notebook folder will be a little bit different. Okay, cool.
Thank you.
No problem. Okay, guys. So you might be asking yourself why the last minute, are we switching to using Domino? Well, it's your last week of the class, and Domino has very graciously agreed to give us some free compute to do a trial of this. So you're our guinea for teaching in the future. Hopefully for you, this is also big. I've seen clients at Deloitte use this all the time. It's a really, really sophisticated platform for doing data science. It's the ones like System. So today's lesson is going to be all about predicting the future. And even we use downstream, like numbers, are built these kinds of ideas that work matters, that the sequence matters. So if we layer in this idea of a time series, or not just how where our data points exist in time. That could be something like a date, a timestamp, or something else entirely. So may not just consider their direct order, but how far apart the different time steps are, and any of the entries within the time series. Okay, JC, well, that's a lot of just information, but what the hell does that mean? I want to show you some sequence modeling and some time series with just plain old regression first. So you can kind of build some deeper intuition for the data structures and the techniques that we have used historically for these types of problems. And then talk about why they break down, and then introduce some of the more sophisticated neural network techniques that we're using today. So let's set aside recurrences for just a minute and start with something really, really simple. We're going to use fake stock market data, and we're just going to generate that using a series of list comprehensions. So from NumPy, from random, we're going to generate a month's worth of data, 28 days, short month, a February month, if you will. And then we're going to take a random draw plus a day times random for day and days. Okay. Why did I write the function like this? That's essentially because as time goes on, right, as the number of days increase, this number gets larger and larger and larger. So as we go further in time, our data grows. And you can see our list of stock prices here. Take a quick peek at a visualization of the data. You can see a very clear positive linear relationship, right? As we add an additional day in the month, stock price seems to go up. Further and further in time, the price is going up and up and up. So we're going to try just a simple linear regression on this to see if we can establish the coefficients on the model. Okay, right now our data is shaped just as a simple NumPy array, but we need X to be reshaped as a column vector. So right now it's flat. So we're going to just do a quick reshape so we get something that looks more like this. Okay, that's nice and clean. We've got a column for each day now. We're not going to do this by hand. We're just going to use tried and true linear regression from scikit-learn. Pretty good. We got an R squared of 48, almost 49%. That means that our model explains something like roughly 50% of the variance in our data. It's pretty good. Pretty good. Okay. But that's not a very realistic model, right? We just have the day of the month and the stock price. We're going to add in some other information as well. Make the data a little bit more realistic. Okay. So we are going to generate a empty array called stock data that's going to have 4 columns and 28 days. Okay, length of days, 4 columns. Our 4 columns are going to be assets, liability, the quote of the stock, and then the actual day of the month as well. Okay. Now I got some beautiful looking column data. You can see our day here expressed in scientific notation. Yeah, always kind of fun. Let's take a look at the data again. So we're going to take a look at the day and the stock quote. Now, if we just tried our old model again on days and stock quotes, it's not bad. Okay, it's different. Our R squared here is different because we're using a new set of generated data. But we just use the same modeling technique where we're just using 2 variables, 1 input, 1 output, using days and fitting that on stock quotes. It's not horrible, but can we do any better? Okay, so let's include the information from our asset, liability, and quote columns. Yeah, of course, that worked, right? The other covariates, the assets and liabilities, also have the information we care about. But if we excluded the day information, that time series data, our model's performance drastically decreases. In other words, time is important to our model, which we know from creating the data artificially, but it's something that's also intuitive, right? If I'm actually studying stock prices, and I'm doing some quantitative trading, time is important for relative to the stock price. Time series is a very, very well-established econometric technique. It's been around for a really long time, and so there's a lot of jargon around time series. There's a really, really nice handbook published by the government on time series. So if you want to read through some of the major time series approaches, autocorrelation, stuff like that, you can read this book linked in the notebook. Okay. I'm going to highlight a couple time series techniques for you. Again, the reason we're highlighting these techniques is to show you their limitations when we start to talk about other types of sequence modeling. So one time series technique, so before, the only thing we've seen is just using day as a variable in our model, which works moderately well. There are other techniques, though. We could use something called a moving average, or a rolling average, or running average. Probably heard these terms before. And convert our stock quote data into a rolling average and use that in our prediction functions. This is like, think about it this way. If I'm trying to predict today's stock price, then I might look at the stock price from the past 3 days. Well, that's a lot of Python for us. You know, the sum of stock quotes times the index plus 3 divided by 3, 4, blah, 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 blah. Okay. Pandas has some nice features for rolling averages for us already. We just do rolling and then provide the step that we want to use. Pandas was actually invented for time series analysis. Wes McKinney developed Pandas while working for some major bank in New York to do some quantitative trading analysis, so it's extremely well suited to time series data. Then we get our rolling average. You notice the first two are blank. That's because there aren't 3 days in this time window to look back into. So that was rolling average, moving average. Next term I want to introduce you to is forecasting. Forecasting is just simply predicting the future. So that's taking information about stock data, our quotes, and predicting a particular stock price. That's a model-based approach that you saw me use here in this line of code, right? We're fitting a model, then we're just predicting it. Another way that I've already mentioned, but just reinforced, is that we could use the series from the prior day or the prior observation to make a prediction about today. And you think about the intuition for this, like if I wanted to predict what the weather is going to be like today or tomorrow, I could use today's information to predict tomorrow's weather. If it's 70 outside and sunny, it's probably going to be 70 outside and sunny tomorrow, more than likely. This is the idea of using our rolling average or moving average inside of our model. That's the idea of using information from a prior observation or prior state. Okay. Now, we can look at 1 day, but maybe to create a better prediction, I can consider more than one observation. So I increase the size of the window and use that. And you can see that my model performance increased when I increased just looking at from 1 day to looking at, I think 2 or 3 days. I can't remember, 2 days. Okay. Another technique, instead of using a rolling average, is to use something called exponential smoothing. So rolling average may not be entirely accurate all the time because there might be spikes in the data. Right? You can think about using that weather example. There might be 1 day in DC, the DC weather is horribly unpredictable. Be 95 1 day and 60 the next. It's actually about what's happened over the weekend. It was like 75, 77 and sunny on Saturday, and then it was 55 and rainy on Sunday. Very variable. One way to combat that, if you're using that information rolling average, is to use a technique called exponential smoothing. And essentially, you just smooth the mean using an exponentially decreasing past weights to predict the future. Okay, that means the further back in time, the less important things are. Could roll our own, but of course, Pandas has a method to do this. Create an exponential smoothing column. Again, that's a parameter I can pass to my model if I wanted to. Yeah. Last time series term for you before we move on into the more exciting stuff. Seasonality. So these are the effects by day of the week, the time of year, holiday, day of, is it a weekend? Is it not a weekend? Is it tourist season? Stuff like that. Okay. Winston was asking me about the exponential smoothing function here. Okay. The half-life parameter. I think, is that really what you're asking? What does this half-life parameter do, Winston? Yeah. Half-life is how, basically if I go back 7 time steps, like what is half of the weight gonna be? So half of the weight that it's using for the observation that it's predicting is at 7. Yeah, exactly like nuclear decay. Yep. So just to show you the effects of some seasonality in fake data, let's say that a store sells more stuff on Sunday. Could be some kind of like after church restaurant, or who knows exactly, but they sell more crap on Sunday. And we can do that by just using modulo 7. Actually, one of my favorite operators in Python. It's always fun. Pop quiz. You guys know what the modulo does? Yeah, the modulo returns the remainder. Okay. So in this particular function, right, the day divided by the modulo, I'm going to sell more stuff later in the week, times random for days a week. Okay. So if I just pass the day raw into our model, then our model is kind of mediocre. But if I do use the day of the week as a feature using days modulo 7 like we did in our function and add that as a feature into the model, our model's performance automatically increases pretty quickly. That's pretty common when we talk about forecasting techniques. Essentially, you want to make sure that we have some kind of representative feature, especially for seasonal trends. Like you don't want to make a prediction for Christmas Day in a model for like a Target, because Target's closed on Christmas Day, or who knows what the store is, but those types of models won't generalize well if you're not controlling for seasonality. I will say, forecasting is a very important technique to learn, especially for business uses. Like being able to forecast a budget, being able to forecast your portfolio performance, all really, really fun and important stuff to know how to do. I've used a lot of forecasting for predicting customer wait time in hospitals. It's been one of my big projects that I've worked on for clients before. And I used a lot of forecasting techniques. How many people are in line? What time of day is it? What's the season? Is it cold season? Is it flu season? All kinds of crazy stuff. Perfect. Well, there's plenty more I could teach you about traditional time series modeling, but to be honest, it's not as exciting as the latest and greatest in recurrent neural networks. So time series is really great for traditional quantitative information like stock prices, especially where you want to have some understanding of what the relationships are. Because when we go into neural networks, it's a little bit more of a black box. But why recurrent neural networks have become popular is that they're really good at modeling this idea of a recurrence. So a recurrence is simply a mathematical term or mathematical relationship that we use to define some kind of recursion in a sequence. It's like the Fibonacci numbers are a really famous recursion or recurrence. Okay. So in the Fibonacci sequence, we might use something like f0 equals 1, f1 equals 1, so on and so forth until we build the whole sequence out. But when we're talking about neural networks, what we're talking about are essentially loops. So we have some state that's called h of t. Okay, t is the present. Now h is little h without any subnotation is all states, and then you see this loop v. Okay, sometimes you'll see this notated as like a square block with a loop instead of just the loop. But essentially, this is what we call a folded neural network. Okay, when you see this notation, it's folded up. The recurrence is all expressed in one graph. Okay, I've got my x inputs that are associated with u weights. I've got my hidden state associated with w weights and o output. Okay, along with all the other weights of the state at v. Now we can unfold everything and you'll see the different hidden layers. Okay. The hidden state at t minus 1 with the input layer of t minus 1, u. Again, the u and w and v are all weight matrices. And the information flows from one step or one recurrence to the next. Recurrent neural networks don't have to have any set fixed length, which makes it possible to model any function involving recurrence as a recurrent neural network. Whoa, wait, what? Let's unpack that a little bit. Let me repeat it again. Essentially, any function involving recurrence can be considered a recurrent neural network. So that means that we can go well beyond just predicting stock prices or just predicting the weather. Some other sequences that you can begin to think about. Text. Text is a sequence, right? One word depends on the next word, and the next word after that depends on the previous words. That's a sequence. That's something that we can model using recurrent neural networks. Okay. Stop and think for a second about some of the other sequences that you could model. So some other properties of recurrent neural networks that are important to remember. So again, regardless of sequence length, the learned model always has the same input size. So no matter how many of these time steps we have, the input size of X is always identical. That's because the model is not specified directly as a function, but as a series of transitions from one state to the next. Right? This process here is a specification of transitions. The other thing to note as well, and this is the very handy property of our models, is that it's possible to use the same transition function at every step with the same parameters. That means I could use the same weight matrix again and again and again. Like, okay, well, why is that important? It's because it makes a single learning model possible for time. Right? We can model a sequence because regardless of the length, the input size is the same. And we've modeled a series of transitions. And because those transition functions can share the same parameters over and over, these two properties makes it possible for us to learn a single model. Okay. Now, there are a lot of different recurrent neural network architectures, and we could go on and on about all of the major recurrent neural network architectures. There are three major design patterns that I want to talk about just briefly before we go into LSTM. The three major kind of design patterns, if you will. One is that a recurrent neural network produces an output at each time step. Okay. So in this example, it's going to use this output. This output is going to feed into the next state. That's one major architecture. Second major architecture is that the recurrent connection only from output one step at a time to the hidden units at the next step in time. Okay. What that means is, so the previous example, we just produced an output and then we created a model directly of the output as an input into the next. So like flow down, flow up. Second architecture then is that the output goes directly into the hidden state here and considers that as part of that state. The last model, which is I think probably the more common one, the last major architecture choice, is to have recurrent connections between the hidden units that can read an entire sequence and produce a single output. You know, if I'm thinking about the text world, right, that means that I could read an entire sequence of in length and produce a single output. So if I'm trying to predict what the next sentence is going to be, I can give the model a single sentence and it produces the next sentence. All right. So this model up here is just a generalization of recurrent neural networks at the highest level possible. I could fit a model like this, no problem. But let's break it down into the more popular model. We call this whole thing a loop, right? Each one of these is a loop. And then that's a unit of a loop. One particularly successful architecture of these loops is called the long short-term memory. Essentially, what long short-term memory allows us to do is to both remember things in the long term, but also have heavy weight on what's happening frequently. So what's happened in the past with neural networks and some of the impetus for long short-term memory is that if you're considering very, very long dependencies in time, you run into this problem with a vanishing gradient, okay? So those vanishing gradients can be so tiny that they become zero. And RNNs have notoriously had struggled with that problem until we have LSTMs. Okay. So here we introduce a new parameter that's called C. Okay. That C parameter, essentially quite a learning rate, but basically think about it of how far we want to look back in time. So we've introduced this new C parameter into our model. And now I can look just beyond the state of HT. See my activation functions here. See a lot, we got a lot going on. You can see our C parameter, C at t minus 1. Right. I wish I had I need to redraw this graph for you guys. Actually, I wonder. That's not the right color. Let me see. All right, sorry guys, that was not helpful. Clear all drawings. Okay. And if you have, I don't want to go way too deep into this. We'll talk about this a little bit more when we get into the code. If you have questions about this, feel free to reach out to me, talk through this, and I'm going to provide some recommended reading on this architecture. But essentially what you can take away is we're considering that there's some kind of other parameter that we're training to consider how long to look in time as well. So, I've talked about how LSTMs have overcome the vanishing gradient problem. Okay, cool. I mean, what does that mean? Well, overcoming that vanishing gradient problem has allowed us to address some really, really cool things, like dealing with text data. Dealing with text data using time series modeling like we were doing before was not possible. Modeling those sequences and dependencies was very, very difficult for traditional econometric techniques. But these networks, right, can consider those dependencies in a much, much larger time horizon. And it's good at that because language is inherently ordered data. We talked about that. Letters, words go after one another in some kind of predefined way. But there's so many possible combinations. It's not even feasible for us to imagine all of the possible combinations. So we can build these complex probability models. We're going to implement a LSTM and Keras. We're just going to try and predict the IMBD sentiment analysis. So like how well the movie did using our LSTM. We're going to do 2 implementations of an LSTM. We're going to do one with Keras really quickly, just to show you that Keras can wrap most of this stuff at a pretty high level. All the documentation is here if you want to dive into it after the class a little bit more. A lot of this particular example is drawn from The Unreasonable Effectiveness of Recurrent Neural Networks. You can read this blog post. I highly recommend reading this after today's lecture. All this stuff. I'm going to go ahead and kick this off. While I talk through the code. Okay, perfect. Yeah, and go ahead and kick this off if you haven't already. It'll take a couple minutes to train. So we're going to import standard models, our sequential model, our dense layer, and embedding models. Okay, that's nice NLP model for us. And then import the LSTM layer. An IMBD is a baked data set from Keras, which is very handy. Dimitri asked if these notebooks automatically use GPUs for training when you select a GPU backend. The short answer to that is it depends on the Python package you're using. So like in the example below this where we're using just vanilla NumPy, no, it doesn't know how to use GPUs, but Keras and TensorFlow use GPUs automatically. I think the other thing you can do too is if you know you're on a GPU environment, you can set that parameter or import the GPU versions of some of these directly as well. So that way it's explicit. We're going to set the max features in our model to 20,000. We're going to cut text after this number of words and just use the most common words. Our batch size here is going to be 32. Okay. Max length of any word is going to be 80. Okay. We can load in our X and Y directly from IMBD load dataset feature. And we get the length of our training sequence and the length of our test sequence, 25,000 in train and test respectively. We're going to pad the model a little bit. Okay, wait, what does that mean, John Cody? What does pad the sequences mean? Essentially what we're going to do is just stitch this stuff together so that our sequence is maximum of 80 words basically per time step. And do that both for training and testing. Here's our actual model. Okay, so we're going to build a sequential model. We're going to add an embedding layer, which has 128 vector representations. So that's our input, our text input. Okay. Then we're going to use an LSTM with, again, 128. See what we did there. Feature inputs, dropout rate of 20%, and recurrent dropout rate of 20% as well. Then our last layer, our output layer, is going to be dense with an activation function of sigmoid. You can try using a whole bunch of different optimizers for this particular model. We're using pretty much standard stuff, binary cross entropy and atom. Binary cross entropy for loss and atom for optimizer. And then, of course, we've got our model.fit, our xtrain, xy, number of epochs we're going to pass, as well as our validation stuff here. So our model is running. I think it's a natural place to take a break really quickly before we get into evaluating how well our model did. And then I'd like to come back. If you have any questions about this code, feel free to add them in Slack while we're kind of waiting for the next thing. We're actually going to get into, Keras abstracts away the LSTM process here. We're actually going to get into what this line of code does in NumPy after we come back from the break. I'm going to talk about the process a little bit more so you guys understand what's happening under the hood. But I'll stop there. We'll actually take a 10-minute break because it'll take a while for this model to train. And then we'll come back and talk about it in just a few minutes. Go ahead and pull up the timer. Okay. Let's come back in 10 minutes, everybody. All right, team. Let's get going again. Let me see how our model is doing, everybody. Winston's is still pretty early on in the training process. My notebook seems to be stuck. Maybe we are heavily taxing Domino. My laptop is definitely struggling. Okay. I'm only at 4 out of 5 epochs as well, I think, and that is a-okay. Given the size of the data set, probably what's likely is that our model is not going to outperform something like TF-IDF on this particular data set, just because we don't have a ton of data, which doesn't make it very exciting. Right? This is a simple classification task. We're just trying to predict whether or not this is going to be a positive or negative review. And so it's not the end-all be-all. I just wanted to show you that it's possible to do LSTM and Keras pretty simply. You can go ahead and kill your kernel. I think the accuracy just from running this a couple times is something around 50 or 60%. It's again, not the world's best. You can go here and interrupt your kernel up here. Okay. Next thing you need to do is make sure to go ahead and install Newspaper 3K. I've already done this. You might have a different output here. You run this as well. Okay. So this part of the class is going to be the most fun, I think. We are going to generate text with NumPy. So we're going to take our LSTM structure or our RN structure. We're going to analyze a sequence of text, and we're going to go beyond just classification. We're going to generate text. It's really fun. We're going to pull some stories from today's news from the Associated Press. That's what this Newspaper 3K library does. Okay. It's going to go out to apnews.com and grab articles. Take a second to load. Got 84 articles. I did this morning. It was only 71. Let's take a look at some of the articles. Oh. .txt. Okay, never mind. I guess the first couple are blank. So what we're going to do is we're going to grab just one of the first articles, parse it out, and grab the text from that article. Oh, man, seriously? Okay, here we go. Okay, here's the text of our article. The one I pulled this morning was about like the Chinese tariff situation, so it was way more fun. This is not as exciting. Okay. This looks like a test drive of an autonomous Lincoln MKZ. Okay, so we just have the text of this article. Now there are a couple things we need to do. We can't just throw raw text at our model. That won't work, right? We need to do some kind of transformation. So we're going to do a couple transformations that are based on an implementation in the unreasonable effectiveness of RNNs. That's the article that I referenced up above. We're going to do this whole process in NumPy. So we're going to take our article text, which is this. We're going to split it up into individual characters, make it a set. And when we make it a set, essentially what that's going to do is remove any duplicate characters. Then after it's a Python set, we're going to turn it back into a list. Okay, so an article string is treated essentially as a list underneath the hood, an immutable list. That's a difference in Python strings. We're going to take that list, turn it into a set, and which removes duplicate characters, and then convert it back to a list. Okay. Once we have our list of unique characters, we're going to just compare it to text size. Okay, so we have 39 unique characters, 583 individual characters in the text. Okay. That means that our text, just to think about this take a step back, right? This article is a sequence of 583 length with the repetition of 39 possible values that compose the sequence. Okay? That's how we're modeling it. So we're not modeling words like we would in TF-IDF. In this model, we're going to model things as characters. It's more fun that way, right? Model the characters, not the words. You can totally change this up and model words instead of characters, or sentences instead of words, or phrases. I mean, however you want to do it, that's up to you. A stretch goal today, when you're implementing your own model like this, you could change the implementation to focus on predicting the next word instead of predicting the next character. It's a little bit it's a little bit easier for us to work on predicting the next character, though. That's why we're using it for the example in class. Okay. So in order for us, so even if we split the data into our characters, which is a list, it's still not in a way that we can use it in our model. So we're going to do a couple different transformations. One, we're going to one-hot encode the characters as numbers. Then I'm going to take those characters and flip the dictionary around so that we have a lookup table of integers to characters. And then I'm going to apply that to our text data and integer encode our data. Okay. Well, what the hell does all of that mean? So if our data is 583 characters long, there are 39 possible characters. Here are 39 possible characters, where H corresponds to 0, Y corresponds to 1, G to 2, so on and so forth. Now, this isn't useful for us directly. So I flip it around so that I have a lookup dictionary where the integer is the key and the value is our character. Then this list represents the sequence of our text. So 13, okay, let's look up 13. 13 is T, okay. If we go back up to our text, the first letter in our sequence is T, the, okay. And same with like the last character. If the last character is N, right? 33 is the last character. If I go here, oh, 33 is our period. 14 is our N. Then this sequence is actually what goes into our model, okay? Not the text data, not the character, not some TF-IDF value, this sequence. And this sequence could be any length. That's one of the powerful aspects of recurrent neural networks, right? We're not modeling per se the sequence itself. I'm just modeling the transitions. Trista asked if I should have used string.lower. Yes and no. For this example, and you'll see why when we start to generate some of the text later on, is it's kind of more, it could be more interesting to leave it uppercase. But as a pre-processing step, absolutely, yeah, that might be something that you want to do. And it's something you could play around with later, Trista, too, when you're doing this yourself. Okay. So let's get into our model. So we're going to look at a model with 1,000 different iterations. We're going to look at a training sequence length of 40. That means as I train my model, I'm going to consistently look at a sequence length of 40. I'm going to look at a batch size that's a direct relationship of our training data size and our sequence length. And I'm going to use 500 hidden layers of neurons and a nice tiny learning rate. Now, there are 3 weight parameters that I need to initialize. One is our input weights to the hidden layer. The second is our matrix of hidden weights to hidden weights. And our third is our parameters for the hidden weights to the output layer. Okay. WXH, WHH, and WHY. Okay. And you can see all of this stuff when you start to think about it, right? This first array is how big is our hidden size and how many numbers of characters are there. There are 500 hidden layers. There are 39 characters. That's what the size of our matrix is going to be. the weight of our hidden size for hidden size is just 500 times 500, right? And then our output weight matrix is the number of characters to hidden size. We're going to add 2 layers of bias as well. I think you talked about these parameters with Aaron last week, adding in a bias into your model. This is typically just 1. I don't think, rarely, if ever, have I seen someone use a hidden bias that wasn't 1. But this parameter exists as well, just for your awareness. Other things that you may not have thought about, because we're modeling this as a transition of sequences and we have kind of a cold start problem, right? We also need a random set of information about the previous state. So we're going to initialize a kind of empty array about information from the previous state. T minus 1. So if T is the present, T minus 1 is the state right before our current state. And this is all going to be zeros. We're not initializing with any particular weights directly. Should run that. If there are any of the objects that you want me to inspect on the hood or have any questions about what these objects are, feel free to ask. So recurrent neural networks and LSTMs in particular can do both forward and backward propagation. So in the model we're about to do, we'll make 1 forward propagation pass and then we'll make 1 backward propagation pass and then look at the gradient after that. So our forward propagation pass is going to take our inputs, our x's, and our targets, as well as this information from the previous hidden state. So since the RNN receives the sequence, the weights are not updated during one sequence. Okay. They're updated a little bit later on. So we're going to have our data here stored as a dictionary. Okay. The X is the sequence, the hidden state at the sequence, the Y at the sequence, et cetera, et cetera. Okay. We're going to copy the previous hidden state vector, the weights, right, into hidden state minus 1. Okay. Then we're going to initialize this particular forward propagation pass with 0. Then for each t, so that's our time step, for each time step in our length of inputs, so that means for each character in our input, what I'm going to do is take my t time step, initialize an array of zeros. I'm going to set my x inputs of t 1. Okay. Then I'm going to figure out what that hidden state parameter looks like. Okay. When is it activated? Figure out what the unnormalized log probabilities are for the next character based on the weights calculated in this step. And then I'm going to normalize the probabilities for the next character here. Okay. Then I'm going to run my softmax and get the sum of probabilities is for those particular examples and update the loss. Okay. One thing to note is that the sum of probabilities, even without the exponential function, well, excuse me, the sum of probabilities is 1 without using the exponential function, but all of the elements are positive through the exponential function, kind of underneath the hood here. I bet, I know that this, you guys talked about this last week with Aaron, with back propagation and forward propagation. Neural networks are not as hard to implement as you think, right? Even if you look at like underneath the hood of some of the models that are pre-baked, like this stuff is not as surprising as you would think. It's just basically a whole bunch of matrix algebra. So that's our forward propagation function. We also want to look at our back propagation function. Okay. Basically, it's everything we just did in the previous step, but just reversed. And the D in front of everything means basically derivative. I won't belabor, in the interest of time, I don't want to belabor the back propagation too much because it follows very similar steps. And then here is our model. So let me go ahead and kick it off. It's going to take a minute to train while we talk through this code. Okay, there we go. Cool, cool. So data pointer, this is something we're just going to hold in memory. This is something we're going to update as our model goes on and what part of the sequence we're evaluating as we go through the model. Now we need to initialize a couple memory variables for our gradient descent. That's what autograde is, just an implementation of some kind of gradient optimization. So we're going to have a memory of the weight matrix for X to the hidden layer, a memory weight matrix for hidden layer, and a memory weight matrix of the hidden layer to the output layer. Initialize all of that crap with a whole bunch of zeros in the shape of the previous matrices we created. And then we're also going to create our memory matrices for the bias layers as well. Okay. Now remember before we set the number of iterations equal to 1,000. So for I in range of 1,000, we're going to make updates to these weight matrices. Okay. So first thing we want to do in any iteration pass is update our H previous state. We're going to in other words, we want to reset the memory of our recurrent neural network. So an iteration is an entire pass over that particular process of estimating the weights. We're going to do it again and again and again and update those weight matrices for our gradient descent, our memory matrices. Okay. And I don't remember what we set our batch size to. What did we set our batch size to? Let me see. Oh, that's right. It's a relationship of our text data size to our sequence length. Let's see. Let's do a quick check for understanding. Do you guys know why the batch size is a relationship to the sequence text data size to the sequence length? Yeah, think about what this function does, right? If our sequence length is 40, okay. Any guesses, guys? And gals? So Trista has an answer. Batch size is the number of examples needed to train on, and text with larger character length has more examples. So the first part is not quite right there, but the text with longer character length has more examples. Yeah, you're kind of getting at the right answer. I want to see. It looks like Mac's still typing. So Mac, if you want to chime in, and then I'll go over. Sorry, I wanted to print out batch size for you guys, but my model is still running. All right, so if you think about batch size as our text data size divided by our sequence length, in other words, how many sequences of the length that we specified exist in our text data? Okay. Now, that necessarily isn't a whole number, so we need to round that up to make sure that we're encompassing all the possible sequences in our data, right? Because our data set is just one really long string. Now, there are a set number of subsequences of 40 length in that big string. So what our batch size is doing here is just saying how many of those little 40 character chunks exist in our text data. Okay, that's what batch size says in this particular context of this model. Then what we're doing when we're looping over the batch size in our model, essentially what we're doing is we're just looking over the little chunk of 40 characters one at a time. Okay. Now, I think this makes a little bit more sense when we begin to look at what happens with the data pointer. So remember, with our data pointer is equal to 0, and then for each of our B and our batch size, okay, our inputs are going to be our character to integers where we start with a certain character in our article text, where our data pointer is up through our data pointer plus our sequence length. In other words, I start at 0, I go up through 0 plus 40. Okay, that's our input. And I change those inputs from character to integers. Okay. I do the same thing for our targets. So my target is to predict t plus 1, or the next batch of 40 characters. So I look at my data pointer plus 1, and then my data pointer plus sequence length plus 1. Okay? Just one character off. This little chunk of code is processing the last part of the input data. Basically, if we don't hit 40 exactly in the sequence length, we just add a whole bunch of space characters until we fill out the end. Okay. Right? If our batch size function always returned a whole number without having to round up. Okay. We make our forward propagation pass. Okay. Then we make a backward propagation pass. Then we perform parameter updates with our gradient descent algorithm, updating our memory matrices. Basically, I'm going to zip all this junk together. We got our parameter, our delta parameters, and our memory. And this is where we're doing our learning grade update. Okay, this is our learning grade here. Okay. Then after all that junk is done, we move the data pointer another 40 characters. Okay. Move the pointer to the next set of data. And then we repeat the whole process 1,000 times. You can see our loss. We started out here at 557, and we've gotten all the way down to 4. Doing pretty damn good. Right? You remember the whole goal of this was to predict the next characters. So let's actually do some prediction. We trained a model while we were talking about this function and what it does. Our model finished. Well, how do we make a prediction, right? I just got a whole bunch of weight matrices that are probably still really foggy to you. And it's completely okay if you're not 100% sure what the hell this matrix represents, or what this particular matrix represents. That's okay. I expect you to go back and dive through this code quite a bit in the assignments today. You'll probably want to listen to a little bit more of the recording again to go over some of this stuff. And if you're not sure what these particular, well, that's maybe not a good example. If you're not particularly sure what some of these matrices are, you can go back up to this diagram here for the context, right? The weight matrices we're talking about are the directions, typically, from input to the hidden layer to hidden layer, and the hidden layer to the output. Okay. Well, in order to make our prediction, I need some kind of test character. That could be anything we want, basically the first character we want to start with. And then how many characters after the character that we provide do we want to predict? So we trained our model on predicting the next 40 characters, but what happens if this is a variable length input that we can query our model with. We're going to start with our x, create a array of number characters, okay? Right, that's 39, right? That's what we had originally. That's just going to be a whole bunch of zeros. Then we're going to update that x with our test character and set that equal to 1. That's our input. Okay. Then this empty list is going to be just a whole bunch of states. Okay. What are the most common words or common characters, highest probability characters that we should use? This is basically what we're going to return. Then H is our hidden state. We're going to set that hidden state equal to 0 for now. Then for each time step or each character in our sequence that we want to predict our length, it's what we're trying to predict, we're going to look at our hidden state, look at our activation function from our x to the hidden layer plus the dot product of our hidden weights of our hidden layers plus our bias of our hidden layers. Okay, that's going to give us our state. Then I'm going to get our y, okay, just essentially the weight matrix of our y. Then I'm going to get our nice probability function. And the xy is going to return to us the rank of the list of indices according to the softmax probability. Wait, what does that mean? This line of code is going to use our calculations from our probabilities in the previous 3 lines to return the rank 0, or the highest probability character for that position and that length of the sequence. Okay. Then I'm just going to stitch everything back together. Okay, so I'm going to reset our x to a whole bunch of zeros. And for x of ix, I'm going to set that equal to 1. Then I'm going to append our new character together and create our list. Okay. Then the last 2 lines are just to do some pre-printing. And now we can make predictions. So if I start with the T, you can see, not that exciting. I can change the length. It kind of looks like language. It's a little off, but C wasn't in our dictionary. Okay. We can play this all day and kind of see what it predicts. Oh, there we go. Lion, a town. So this kind of looks vaguely like language, primarily because we haven't had enough training data. Yeah, exactly, Mac. It's pretty cool considering we didn't use a lot of data. The challenge for you this afternoon in the assignment is to do better than what we've done here. Right? Didn't use a lot of data because we didn't have the time to let the model run during class. So I wanted to show you how this worked, help you build intuition around it. Now it's your turn to go break down this code and practice. I do want to walk through the assignment today a little bit. So this monkey picture here is talking about a really famous abstract thought experiment in mathematics called the infinite monkeys. Basically, it said that an infinite number of monkeys typing for an infinite amount of time would eventually type the complete works of William Shakespeare, among other things, just pure probabilistically. Some kind of random sequence would arise out of that infinite possibility. Now, we want to see if we can get there a little bit faster using the power of recurrent neural networks in LSTM. So there's a text file linked in here that has the complete works of William Shakespeare. What I'd like you to do is use it as training data for an RNN. Keep it really simple, train it on the character level. That's my suggested initial approach. Then use that trained RNN to generate a Shakespearean-ish text. Okay? Your ultimate goal is to create a predict function like I did in the previous example that can take an argument that's the size of a text, i.e. the numbers of characters on a line, to generate a return text of that size. It's totally, okay, Shakespeare wrote a ton of text. It's totally okay to sample the data at this link. That's totally fine. And then once you've kind of gotten a working example done, then start adding more data. And of course, you can read the stretch goals. And if you have any questions about the stretch goals, you can reach out to the PMs. Okay. I'm going to go ahead and stop this notebook. Okay, my updates. I'm going to stop and discard my updates. You guys won't need them. Stop. Okay. Now, I mentioned that I was going to go over how to do the homework again. So what I'd like all of you to do is in this Lambda School project that you're all collaborating on, go ahead and fork this project. Some of you already have. What I would do is call it Unit 4 and then your name, like Unit 4 underscore, click on Mac workbook or workspace. Something that we know that it's your Unit 4 workspace, okay? Go ahead and fork it. Do your assignment. Go ahead and fork. Okay, I forked the project. Then when you're done, what you can do is you can save the changes and submit them for review. So let me create a change in the README, something like hello world. Click save. Okay. And then once you've done your assignment today, you can hit request review and just say, hey, you've updated your assignment. Updates to Monday's assignment. And create a merge request. Then we'll be able to look and see your work on your assignment. Okay. All right, guys. I will go ahead and close out there.
I missed that completely.
I'm sorry, what did you say, Winston?
I missed completely how to get the separate workbook.
Okay, gotcha. Yeah, let me go over it one more time. Okay. So if you go to the go to projects, collaborating projects. Take a second to load. Okay. Click on this project. You'll be in this kind of landing page.
Still spinning.
Okay. Okay.
Okay.
Okay. Then click on fork. Okay. Create a name for the project. Use something that we'll recognize, like Unit 4 underscore Winston workspace. Okay. Fork it. It'll automatically open that new workspace you've created. Then once you do your assignment, you can just make any update directly. So like, oh, hey. When you actually do the work in the Jupyter Notebook, it'll save. Then what you can do is you can say request review and just say submitted Monday's assignment. Then create merge request. And that's what you have to do to submit today's assignment and the assignments for the rest of the week as well.
Thanks.
No problem. All right. If you guys have questions, I'll be on Slack to kind of answer questions about the workflow and questions about the content for today. I will be joining office hours on Tuesday and possibly Wednesday as well this week. I don't think I can do Thursday. But looking forward to working with you guys this week and being back. Yeah. Thanks, everybody. Have fun with the assignment this afternoon. Shakespeare is always fun. All right. Enjoy lunch. Bye, team.